All right. There's somebody found calculus. Good. I think we got them all. All right. Nice. All right. So today we're going to be talking about limits. This is the last lesson in Unit 5. It will bring you right into Unit 6. This is something that we don't normally talk about a lot in Algebra 1, Algebra 2, geometry. It is the building block of calculus to be able to understand limits. So we're going to spend a little time on it today. Oops, let me get my pen straight. Oh. Well, I'm glad to have you with us, Aram. Okay, so we are going to be talking about what a limit is. We're going to have to review what a continuous and non-continuous function is, because that's really important for limits. We're going to talk about the symbols we use for limits and how to find limits for different cases, continuous, non-continuous, and how to find them graphically. Let me see if I had a little reminder. Here we go. All right, a few reminders. Make sure you're checking your pacing. You got school ends on June 14th. We will have a couple more learning labs, and then we're done for school. Summer will be here. I am offering an end-of-year incentive if anybody wants to take me up on it. If you complete all of the assignments in the class by the end of the day of June the 12th, I will exempt you from taking the final. All right? That's nice, huh? Yeah, it's a deal, huh, Lonnie? Yeah, because I know you guys are all busy. All of my students in this class have a lot of other classes that they're taking. And if you can get all of your advanced math assignments done by the end of the day, June the 12th, I'll just exempt you from the final. All right. So remember, it ends on June 14th. So we should be finishing up Unit 5 this week and getting into Unit 6. You will get an exemption, which means it just won't go into your grade at all. It'll be like it didn't exist. So, yeah, it'll be exempted. It's worth 10%. The final is worth 10%. So after you've completed all your assignments and you see what your progress grade is, that would be your final grade if I exempt the final. Okay, so as I said, we're going to start limits, and I'm so excited to start limits. It's what I think separates calculus from algebra. It's used for a lot of things. Physics, you're going to see limits. Engineering, you're going to use limits. It really helps us estimate points on, basically helps us estimate a point that we can't see. All right. And it does use special notation that we'll go over that you need to know. Okay, I copied this off website. I wish I put the source, but I kind of like this. And you guys take a minute and read this. And it just kind of talks a little bit about why we need limits and what limits are. So hopefully that kind of helps you understand what a limit is. You did? Yeah. It's funny, Aram. I never really, when I think about dividing by zero, I guess it's a kind of a black hole of math. Um, I never really heard that terminology applied to it, but I think that's a good way of thinking about it. All right, so we're going to be talking about those areas that we can't see that when we start going towards infinity, when we're dividing by 0, those kinds of things. That's what we're going to use limits for. Okay, here's another analogy. I like this one too. You got to pretend you're watching a soccer game, and these are clips from the recording. Okay, you see what's happening at 3:58. Here's this guy, right? And then he's raising his foot over here, but then all of a sudden at 4 minutes you lose it. You don't get that screen. And then over here you see the ball here, and then the ball is in the goal. So what do you think happened at 4 minutes here? What do you think happened here? You see him raising his leg here, and here you see the ball there. The goalie lost the ball. Well, yeah, the goalie did lose the ball, but what did you think about this guy? What was this guy and that guy doing? What did he do to get the ball from there? Kicking the ball. Thank you. Yep, kicking the ball. So that's like a limit, right? So that's what we're doing. If we have missed a little section of our equation, our graph, we have to use what we know around it to figure out what happened in the middle. And Aram's idea, well, maybe the goalie lost the ball, and then Alani said kicking the ball. Well, either one of those could have been the right answer, right? We don't know what happened at that moment. We just have to use what went around it to make our best guess. Okay. So in order to solve limits, one of the key things we need to know is a continuous function or a non-continuous function. So you guys think about it and let me know what you think. What is it? What do I mean when I say continuous and not continuous for a function? What does that mean? You can write it on the board, put it in the chat box. Function that never ends. Any other ideas what I mean when I say continuous or not continuous, or what mathematicians mean when they say continuous or not continuous? Not continuous as in a limit? I guess I'm thinking more in a graphical sense. Like if you saw a graph of a non-continuous function, what would that look like? It will end. How about, let's go into this next page. I got some samples. I'll show you some samples. Here are some various functions that are being graphed. Okay, which one of these would be the continuous function? And here where you've got the open dot, remember that's like a hole when you see an open dot on your graph. These are holes. Except that this one is a hole right here. That one right there is a hole in the graph. Open dot is a hole. So yeah, this last one is continuous. It goes on. There's no holes. There's no breaks. Like this one's obvious, right? We got a break in the function. Something goes on there. We cannot see what happens in that little space. This one was a little bit tougher. Alani pulled it out, said maybe that one was continuous. It looked kind of like this, but I made the hole really big so that you could see there was a hole there, a break in the function. And this one also clearly has a gap, right, in the function. A non-continuous function can have a limit. We're going to talk about that, Aram, how to find limits for non-continuous functions. Okay. The continuous functions, it's fairly straightforward how to find the limit. The non-continuous functions, this is what happens when we start doing things like dividing by 0 or going towards infinity or various things that give us these holes. Okay. We're going to talk about how to find the limits. How do we estimate what goes on in those areas that we can't see on the graph? Okay, so here's some tips on continuity. Polynomials are continuous. If you see something that looks like x to the third minus 2x plus 3 or something, continuous. Okay. Polynomials divided by other polynomials. Remember, we call those rational functions. I shouldn't say they're usually not continuous. I should say they are often not continuous. When we are taking a polynomial and dividing by another polynomial, let's make an easy one, x minus 1 over x minus 2. We're going to run into a problem there when x equals 2. We're going to be dividing by 0. That's going to put a hole in our graph. Okay, so polynomials divided by other polynomials are often not continuous. Any function where you end up dividing by 0, not continuous. If your function divides by a trig function, so let's say we had x squared divided by cosine of x. If you're dividing by a trig function, it is usually not continuous. Because any of those trig functions, remember when we graph them, they keep intersecting at 0. Okay? And we will get a circular zeroing going on. So some of the functions of that will lend us into 0. Okay, a function can be continuous in a limited area. Check which area you're interested in. So let me go back to this, our pictures. This, this one, number 3, not continuous, but if we were only interested in this little area over here, that area is continuous. So make sure you understand what area you're looking at on your function. So you guys, any questions on what's continuous or not continuous in a function when you're graphing it? You're looking for holes, you're looking for gaps, you're looking for spaces. Or asymptotes, like I think Aaron was referring. So like if you're coming up here and you're just going right along the edge, but you never quite reach that, that you have an asymptote there, that could also, you need to be able to figure out its limit. Okay, so those are your tips. All right, so take a moment and open Desmos.com on your computer, and I need you guys to graph this function. I'm going to write it down, and I will open it on mine as well. Graph that function on Desmos if you've got another window available. Did everybody get it? You might need to zoom in to see this. Give me some kind of signal if you've got your graph up on Desmos. All right. Yes, John does. Lonnie does. Okay. All right. So looking at your graph, you want to hover over where x is equal 2.5. What value do you get at x is 2.5? You know, remember you can go along that graph and find it. I get something close to -8. Is that what you guys got? -8-ish? Yes. Okay. Perfect. How about if you're at 3.5? Get a -8.6. Is that what you guys got? Oops. I gotta go back to Desmos. I'm flipping screens. 3.5. Got a bigger number, like close -4-ish. Yeah. Negative 3.875. All right, so if we were trying to find what value this graph was at 3, and we looked at 2.5 and we looked at 3.5, we have a pretty big space between those two numbers, right? Negative 8-ish to negative 4-ish. You know, that's pretty tough. So if we kept going in closer and closer and closer, our numbers would get closer to each other, right? So go ahead and tell me what value you get at 3. What value do you get on the graph at 3? Negative 7? And while you're there, kind of push around some of those values and see how close you have to get to some of those other ones to see. If we'd been at 3.04, right, we would have gotten negative 6.8. If we'd been at 2.84, we would have gotten negative 7.5, right? So slowly, if we get closer and closer and closer to the value we're interested in, we would get closer to the actual number, negative 7. Okay. Now, when you're looking at limits, tell me, is this graph continuous when you graphed it? Did it look continuous? Were there any gaps, holes, breaks in the graph? It's continuous. Perfect. All right, so when you decide that your function you're looking at is continuous, and it asks you to find a limit, for example, if it said find the limit, and this is how we write it, as x approaches 3 of x to the 3 minus 5x squared plus 7x minus 10, if the graph is continuous, if that's a continuous function, you find the limit simply by substituting in the 3. Okay, so we would have said that our limit was equal to, I think Aram said negative 7. Okay, if the graph is continuous, you just plug in your desired value to find your limit. Really straightforward when they're continuous. And let's see, I wrote that on the last one. So limit notation, we want to use that limit. We take whatever our variable is approaching. And then here's our function. Okay, is equal to some value. Usually they use a capital L to indicate what the value is. All right, so here is how you would write it. There's a number L such that the value of f of x gets closer and closer to your value of L as x approaches some number A. Okay, so L is called the limit of f of x as x approaches A. Okay, this is the symbology you need to know. This is what you'll use to do limits. Right. All right, so let's try a different one. Take a moment in your Desmos and graph this x squared minus 9 over x minus 3. And tell me if it's continuous. And when it's continuous, let's look at this first before you graph it. What is our exempted value? What can x not equal? What value can x cannot equal 3, right? So when you graph it, I want you to hover over that 3 point and see what Desmos says about when x equals 3. So go ahead and graph that. It says undefined, huh? Undefined. It doesn't make a really good it doesn't make a good hole on that, right? At least when I zoom in, it doesn't look to me like it's showing the hole. But when you hover over it, you'll see that it says undefined. Right? So you want to be aware of that. So is this graph continuous if we have an undefined point on it? No, absolutely not. It's not continuous. So if we were going to try to find the limit of this function, we said let's find the limit as x approaches 3 of x squared minus 9 over x minus 3, we couldn't just plug in the value, right? Because it's going to give us this divided by 0. So graphically, we could look and see what's the value at 2.9 and what's the value at 3.1. Oh, good. Somebody did it. 5.9 at 2.9. 6.1. Probably as we get closer and closer and closer. Hey, Jillian. Nice to see you. Probably as we get closer and closer and closer to that 3, it's going to get closer and closer to 6. Okay. So you could say the value of this one, looking at it graphically, is equal to 6. So that's trying to find the limit graphically. Let's talk a little bit about doing this algebraically. All right, x squared minus 9. What does that break out into? That's a difference of squares. What can we do with that? Hey, Jillian, we're working on the last of Unit 5, limits. So we're just talking about limits. What do we do when there's space, when we're dividing by 0, and we still kind of need to know what the value is at that point? X minus 3, x plus 3, beautiful. X minus 3, x plus 3, that's a difference of squares, right? So if we put that on the top of our equation, instead of the x squared minus 9, we now have this. And what can we cancel out? If somebody wants to just mark up that equation, what do we end up with? Equal. What can we cancel out? Perfect. We just canceled out the x minus 3, didn't we? Whoops. Minus 3. And we end up with x plus 3. Now we can put in that 3 value. We're saying find the limit as x approaches 3. Now that we've simplified the equation, we could put in 3 for the x, and we would get our actual value of 6. Okay, so you can try to find the limit graphically by finding the points closer and closer to the one we're interested in. Or if you can simplify it to get rid of the problem, which in this case is the x minus 3, then you can substitute in. Yes, it is, isn't it? I like that, Aram. Math wizardry. Okay, so again, I want to make sure you understand the limit value. So I wrote it up here for you. Oops. This is the limit as x approaches 3. That's how you want to write it. Little l, lim, x approaches 3 of the function. Okay, it's going to equal some value. That's your limit. Notation. Okay. So, how to determine a limit? If your function is continuous, plug the value in, that's your limit. Polynomials are continuous. If your function is not continuous, try to decompose it. That means simplify it like we just tried it and plug it in. Try to graph it. Use the graph to help you find the value. These are your tips. You can also disregard minor terms and estimate the value, and I'll show you an example of that. So these are 3 things you could try if you end up with a non-continuous function. For a continuous function, this is your definition down here, if it's continuous at the point you're interested in, then you just substitute in the point, the value. All right, we're going to do a few examples off your checkpoint, or I think it's actually off the Unit 5 exam. Oh, wait, nope, this is one I made up. So let's just try this. You guys looking at this, can you find the limit of these 2 functions? All right, so Jillian, we're working on limits. It's the end of Unit 5. If these are polynomials, if they're continuous functions, you just substitute the value in. What is our limit of those 2 functions? They're two different answers. 2, perfect. That's the first one. X plus 2. This is one of your most basic polynomials around, right? This is a continuous function. That's a line, right? That's going to give you 2. You're going to substitute in 0 for the x. 0 plus 2 is going to give you 2. -1, you're going to this 3x plus 1, again, a really basic polynomial. It's a line. It's continuous. We sub in the negative 1, and we end up with negative 3 plus 2 gives you negative 2, right? Perfect. Continuous functions. You just plug in the value. Okay? Remember, you guys, these are just basic polynomials. Polynomials are continuous. All right. This is one that's off your exam. What was the point of this? Finding limits, because we're going to, in Unit 6, we're going to be talking about derivatives. Aram, and derivatives use the concept of a limit. Okay, this is your first stepping stone of calculus, so you have to understand what a limit is. It helps you estimate points that you can't actually see. All right. Oh, the slide before this one. Which one was that? This one? This was just having you try basic limits for polynomial functions. Was that your question? Oh, you don't understand the point of the practice of this? I was just trying to give you a basic one saying, hey, let's find a limit and have you identify that this is a polynomial. No, this is limit 3x plus 1. And the limit as x approaches negative 1. This is a polynomial, so we just put negative 1 in here. Negative 3 plus 1 gives us negative 2. Yeah, okay, so I guess there was a point to that one. And this one is a whole different function. As x approaches 0, we identify that this is a continuous polynomial. We just sub in the 0 for the x to find the limit. I thought you asked me what's the point of limits. Well, I thought, well, there is a point. So, okay, let's look at this one. This is off your Unit 5 exam. Evaluate the limit of this expression as n approaches infinity. Okay. Is this a continuous function? No. Right? We're dividing. We can divide by 0. Does everybody see that? This is our problem spot right here. If n equals 0, we're going to have a hole in the graph. All right, so we've identified that it's not continuous. Can we simplify this? Guys, try to simplify it. See what you get. And what is 2n minus 3n, Alani? What's 2n minus 3n algebraically? What do you get? Negative n, right? So Alani said this became 2n minus 3n over 5n, right? We took out a 2, basically. And then 2n minus 3n gives us negative n over 5n. What can we do with those n's? Can they cancel out? Yep. Those are going to cancel out, and we're going to end up with negative 1/5 as our limit. Makes sense? It's not a continuous function, but we used our approach of decomposing it or simplifying it. Yeah. They're not, Aram, they're not very intuitive sometimes. I remember when I first learned limits, I would try to make guesses. and often I was wrong until I really learned that you just really need to sit down and follow a procedure because they're not always that intuitive as to what the limit's going to be. So this is a case of where it's a non-continuous function, but we were able to solve the limit by simplifying it. Take a peek at this one. All right, 9x to the 4th plus 3 divided by 4x to the 4th. All right, and x is approaching infinity. If you can't see that, it's a little blurry. It says as x approaches infinity. Is this a continuous function? No, right? We're going to end up dividing by 0. All right, can we simplify it? I don't really see a way to do that. All right, so let's go back to our tips that we talked about. Okay, find out if it's continuous. Okay, it's not continuous. Try to simplify it. It doesn't going to simplify it. We could graph it and find the value. That might work. But we could also try this one. Disregard the minor terms and estimate the value. Disregard the minor terms and estimate the value. So looking at this, as x approaches infinity, this 9x to the fourth is going to get really, really big, right? It's going to be a huge number. And this 4x to the fourth is also going to be like a huge number. Okay, making this 3 really irrelevant. Okay, it is nothing compared to as x approaches infinity. That becomes a very, very, very small component of this. So small that we can disregard it, and we can write it as 9x to the fourth over 4x to the fourth. And we can disregard that 3. Aaron's typing something. Does everybody get how 9x to the fourth is going to become huge in comparison to the 3? Yes. Okay. So we get rid of the 3. And now we have a more simple looking equation. Can we simplify this one? Right. So what is our answer after we've simplified this? So it's going to be 9x to the fourth divided by 4x to the fourth. This is a 9, not a very good 9. 9x to the fourth. These x to the fourth, they're going to cancel out, right? And we're going to end up with 9 over 4. 9 over 4 as our limit of that function as x approaches infinity. That makes sense, Jillian? Yep. Kind of. It's hard to get your head wrapped around it. Okay, we'll spend more time on this in Unit 6. It's like I said, it's the first real different kind of thing that we do in as we start calculus. That you normally don't see limits when you study the algebras before that. Okay. So look for irrelevant terms. So Aaron, you have to use your judgment on this. Remember, limits are estimates. Okay, they're not super precise always. So if things approach infinity, look for anything that doesn't have a variable attached to it. Okay, so this 3 didn't have a variable. It wasn't going to change. So as these numbers got really big, this one was just going to stay the same. So look for numbers that don't have variables attached to them. Those can often be disregarded. You're also going to look for ways to simplify. This so far has been fairly straightforward. We've crossed off our variables. They've matched top and bottom of the fraction. You may end up having to factor a polynomial or expand something and look for ways to simplify. You have to put in all your different tools to make it happen. Nope, you don't ever add the 3 back to the limit. This is your limit now. So the limit as x approaches infinity of 9x to the fourth plus 3 over 4x to the fourth is equal to 9/4. That's your limit. Okay, because as x approaches infinity, those terms with the variable got so much bigger than that little 3 sitting there that we just got rid of it. All right. So it may not be a continuous function. Let's look at this one. This is off your exam. So we have minus 2 over the square root of x plus 6 over 9 minus x. And it's asking us the limit as x approaches 4. Okay. This is not a continuous function because when x equals 9, we're in trouble there. But we're not asking for the limit when x equals 9. Okay. All we care about is when x is approaching 4. And is it continuous in the area when x equals 4? You can use a graphing calculator. I know. It says use a graphing calculator to find the value of the limit. You don't even really need to use it. You can graph this on Desmos to make sure that it's continuous in the area we're looking at. We're only interested in that area around 4. So you guys think it's continuous when x equals 4? Is that a continuous function in that specific area? Yes. You can try it on your Desmos if you want and see what kind of graph it looks like. But you'll find everything's defined at x equals 4. So if it's continuous in the area that we care about, we're just going to treat it as a continuous function. So what would be our value of the limit as x approaches 4 for this, given that we think at x equals 4 it's continuous? And I got to say, you guys do not need a graphing calculator to do this one. We just need to put it in our thinking caps. Is it the asymptote when you graphed it? It should be continuous in that area. Okay. If it's continuous at that area and we have a value, all we do is plug it in. So just plug in. There you go. 4 for your x value. I'm going to have to look at what Aram did for the graphing and see if it really... I know, Jillian, but when you get to this point, you can review it. This will be good. You'll say, oh, yeah, I remember Miss Woodley talked about limits. So we go -2 square root where x is 4 plus 6 over 9 minus 4. We're just substituting it in. So we end up with -2. Square root of 4 is just 2 plus 6. 9 minus 4 is 5. -2 times 2 is 4. -4 plus 6 gives us just a positive 2, 2/5. And I think John marked that as the 0.4, right? 2/5 is 0.4. X never reaches 9. Well, not in the area we're interested in. This is what I'm trying to say. This is not a continuous function. And we're like, oh, no, not a continuous function. We got to do something. But then we think and we look and we say, oh, it says as x approaches 4. Well, it is continuous. If we just took that picture just around that 4, that's continuous through there. We just sub it in. It does, huh? Okay. So when you end up with a function, you look at it. Is it continuous? If it's continuous, plug in the value. If it's not continuous, get your tips and tricks, right? Try to simplify it. See if you can disregard minor terms that may not be relevant. See if it's continuous in the area you're interested in. When you do a graph, Jillian, if you end up with like a hole in your graph, or it looks like this, the graph has a break in it, not continuous. Usually that happens when you're divided by 0, or at Aram's point, he said it looked like there was an asymptote. something where we're going off towards infinity, but it's never actually going to touch anything. Undefined. Perfect, John. Great. Aram says this graph has an asymptote at 9. But we didn't care about 9. That was kind of tricky. I thought that was tricky of them, especially when they said use a graphing calculator. And I thought to myself, why? Why use a graphing calculator? We don't care what happens at 9. Okay, so there you go. I think that those are all the examples of limits. I might have put another one in. Oh, here, this is another one. Remember I said trig functions. You might end up with functions that have trig functions. So I want you to take a look at it. This is our function. 1 minus the cosine of x over x squared. I graphed it on Desmos. This is the graph, but where are we undefined on this point? Where is this function undefined? X equals 0, right? So x cannot equal 0. So right here, we have a hole on our graph. Okay. So what is the limit of this function, though, as x gets closer to 0? You might want to do it on your own Desmos so that you can see it, or I put it up here. What is our limit? Looking at this graph as x approaches 0. Your x is approaching 0, so you want to know what your y value is, right? As x approaches 0, what's your y value on this graph? Even though we know there's a little hole right there. Got to watch the scale of it, Alani. This is 1 right here. What's 1? This is 2. 0.5. Yep, 0.5. Right. So as the limit of the function as x approaches 0 is equal to 0.5. This one would be hard to simplify. We can't just plug in 0. I don't see a lot of irrelevant terms as we're approaching 0. This is one that I would say you want to solve graphically. You want to look at the graph and see as you get closer and closer to that 0 point what the value is. So, and I want to make sure you're really good on the terminology. You're going to write limit and with the little l, whatever your variable is, often it's x, as it approaches some number, a, and then you're going to write down what the function is, whatever your function is that they give you, and you'll end up with some value that they usually call capital L for your limit. All right, I think that's it now. Oh yes, this is just a tease for next week. So next week we're going to start talking about derivatives. Derivatives are calculus. So next week we're going to do calculus, all right? And we're going to learn about derivatives. Derivatives use limits. That's why we need to know what a limit is. Okay, so a derivative of a function is defined by this kind of a limit. Okay, and a derivative, if you ever see the little, like a little apostrophe, sure, that is going to be what your derivative is. All right, so go ahead and ask a question. And so you guys were almost done. I got you done early. So we reviewed continuous, non-continuous, what is a limit, how to find limits, and rules and tips for limits. Okay. So go out and have a great week. Aram, if you want to stay and ask a question, that's fine. All right, enjoy knowing about limits this week. Okay. Bye, Jillian. Or unless you have a question too, honey. Sure. All right, bye-bye. All right, Aram, got a question? I may or may not have answers. All right.